It's good to be here today to speak to you. I'm going to tell you a bit about our vision for changing the way that frequency division duplex is implemented in mobile user equipment. First, I'll tell you a bit about who Forefront RF are, because some of you might not know. We're a startup company based here in Cambridge at St John's Innovation Centre, up near the Science Park. We're about 15 people, venture capital funded company, and we're developing a tunable RF front-end module using self-interference cancellation. So the presentation today, I'm going to tell you a bit more about that. Starting with the problem that we're trying to solve, problem with the current architecture in mobile phones for frequency division duplex. I'll tell you a bit about the concept of self-interference cancellation, and then talk about a few different circuit topologies that can be used to address this challenge, and finish with some conclusions, tell you a bit about our product. So, what's the problem with self-interference? Well, in your mobile phone, you're transmitting about, 23 dBm, so 200 milliwatts. And at the same time, you need to receive a signal that's less than minus 90 dBm. So you're looking at 11 orders of magnitude difference in power between the transmit and receive signals. And if you don't do anything about that, then your transmit signal will just leak into your receiver and prevent you from receiving the signal that you want to receive. So if you imagine trying to listen to someone talking and then you start shouting at the top of your voice, all you'll hear is your own voice. And that's what happens in a phone. And today's solution to that is to use a pair of bandpass filters, one for the transmit band, one for the receive band. And the reason you need two filters is that the spectrum that you're transmitting looks like this. So you not only have a very powerful signal in the uplink band, your wanted transmit signal, you also have noise at the receive frequency. And so you need to suppress the in-band transmit signal to prevent it from saturating your receiver. You also need to suppress this noise so it doesn't desensitize your receiver. And so that's what this pair of filters does. You've got your transmit band filter, that's passing your in-band transmit signal, filtering out the noise. And then a receive band filter, which is passing the wanted receive signal and filtering out the high power transmit blocker. And that's what's in your phone today. You've got many of these filters typically implemented at surface acoustic wave, bulk acoustic wave, acoustic resonator filters. And the reason that these are used is that you need very low insertion loss to maintain the efficiency and sensitivity of the system, but you need very high stop band attenuation at close by frequencies. And the only filter technology that can implement this in the size needed for a phone are these acoustic resonators. Now, this was fine for 3G, which was the first modern mobile system to use frequency division duplex. There were only a few frequency bands. You could fit a few of these filters in, and you could have switches to select between them, and that wasn't a problem. But now with 4G and 5G, there are dozens of FDD bands in the specification, and to create a device that supports many frequency bands leads you towards a very complicated architecture like this. Now, I've only shown 5 filters in there. The iPhone supports about 30 FDD frequency bands, so it has at least 30 of these duplex filters, and actually it has more because it has multiple antennas. So you can imagine the level of complexity that you're looking at in an RF front end for a mobile device that supports multiple bands. This increases the cost and the size, and typically it means that devices are not supporting all of the bands in the specification, particularly in devices that are size limited, like a smartwatch. What manufacturers end up doing is implementing different versions of the same product for different geographical regions. So this example is the Samsung Watch 5, 3 different versions of the product, and then each version of that product has multiple SKUs that support different frequency bands. And the only difference between those SKUs is they've got different sets of filters in that are supporting different frequency bands, targeting different regions of the world where those bands are being used. And that leads to stock keeping cost inefficiencies, bill of material inefficiencies, complexities of having to support multiple SKUs, multiple designs to have to actually design and test. And then from a user's perspective, it doesn't support all of the frequency bands. So the watch that you buy in the United States, it might not work when you take it to China because it doesn't have the right filters in it. What we're aiming to produce is a tunable RF front end, so replacing that bank of filters and switches for band selection with a tunable duplexer, which then reduces size and supports all of the frequency bands. What do you need for that? Well, we still need to maintain low transmit and receive insertion loss, high transmit to receive isolation. You typically need 55 to 60 dB of isolation in a frequency division duplex handset. And of course, you also need some filtering in the system because there are out-of-band emissions and out-of-band blocking specs that still need to be met to pass 3GPP standards. But the benefits of this are primarily in saving space. Space is really a premium in a mobile device because by saving space for electronic components, you can put in a bigger battery, you could put in another camera module. And these are things that mobile phone makers in particular are really competing over, is the quality of the pictures and the battery life. For watches, they would be opening up space for other sensors to go into the watch. Again, more product features makes the product more competitive. And this is why there's a drive to reduce space of the RF front-end components, because it can actually make the device more competitive to the customer in this kind of indirect way. And then the other benefit, of course, is that it takes us closer towards a solution where you can support all of the frequency bands in one product and do away with this issue of having global or regional variants, I should say. So now I'm going to tell you a bit about the concept of signal cancellation and how we go about designing a duplexer that's tunable using cancellation technologies. So the duplexer, you can break it down into basically 2 parts. You need something to connect your antenna to your transmitter and your receiver, because obviously you do if you want to transmit and receive. And then there's the canceller circuit itself, which is aiming to cancel out leakage, which is coming through your antenna interface. And so that canceller is taking a sample of the transmit signal at some point in the transmit chain, and it's processing that in some way and injecting the cancellation signal into the receive path to cancel out leakage that has this self-interference leakage through the antenna interface. So I'm going to talk a bit about some different antenna interfaces and cancellers now, and then I'm going to run through some of the combinations that we've looked at. So the simplest antenna interface that you can come up with is actually just having separate transmit and receive antennas. It's kind of obvious. It's simple. It's wideband, or it has whatever the bandwidth is of your antennas. But one of the issues with that is that you've doubled the number of antennas in your device. And for a phone, that's not very attractive. The antennas take up a lot of space. In user equipment, you're also looking to support MIMO, particularly in mid-band. And so you want multiple antennas for doing MIMO. And if you're then using multiple antennas for transmitting and receiving, then the number of antennas is even bigger. They also don't provide any filtering beyond the limited bandwidth of the antenna, so this would make it more of a challenge to meet out-of-band blocking and out-of-band emissions requirements. And the self-interference in this case is just directly transmitted from your transmit antenna to your receive antenna. Another obvious one to look at is a circulator. They have good performance, relatively wide band, and a single antenna, so it meets that requirement. But the difficulty here is they are difficult to implement. You need a magnet or some other special materials, so difficult to integrate, and again, no filtering. And the other issue with a circulator is that they're quite sensitive to antenna mismatch. We're compromising the isolation, so you've got this direct leakage path through the circulator itself. Another antenna implementation is actually a duplexer, like you've got already. It provides filtering and it's potentially tunable, but the losses increase at a narrow duplex separation. Now, I've already said this is what's in your phone already. The difference here is that by combining a duplexer like this with a cancellation circuit, you can reduce the filter specifications of these filters and potentially make them tunable, which is what we've done. So I'm going to talk a bit about some cancellation technologies now. There are really two different types, passive and active, and within those there are various implementations that you can take. This is an example of an active canceller, where you're taking the sample of the transmit signal in digital baseband, and you're processing that digitally, and then you're using an extra transmit radio to upconvert that to RF and do the cancellation in RF. I've shown it here combined with a dual antenna, just for simplicity. The benefit of this is that you've got the availability of high order filtering DSP in order to generate your cancellation signal. So you can do frequency selective cancellation over wide bandwidths and get good cancellation bandwidth, which is useful. But the major drawback here is that you can't cancel noise that's generated in the transmitter. Your transmit radio has got its own noise and distortion, and since you're sampling the transmit signal before it's gone through the transmit radio, your sample doesn't contain that noise, so you have no knowledge of it and you can't cancel it out. The other issue with this is that actually you just need a whole another transmit radio, which is quite big and expensive and not very attractive. And then in contrast, a passive canceller is doing all of the signal processing for generating the cancellation signal passively, and you're sampling the transmit signal at the output of the radio, so at the output of the PA basically, and that means you've captured all of the noise and distortion from the transmit path, and you're able to cancel out noise and distortion as well. The drawback with this again is that there's an extra piece of hardware, but specifically the wider the bandwidth that you want to cancel out, the more hardware you need. So if you imagine the self-interference coupling has a kind of coherence bandwidth, it varies over frequency. The wider the frequency you want to cancel, the more variation you're going to see in that cancellation channel, the more variation you're going to have to replicate in your passive canceller, and so the more components you need, the higher order filtering you need. And this is a third variant of a passive canceller, shall we say, which is kind of combining the antenna interface with the passive cancellation in one circuit. So this is called the electrical balance duplexer. And the way it works is that your transmit signal is split coming into the hybrid junction here. Half of it goes to the antenna, half of it goes down to this balancing circuit. You get a reflection due to the antenna mismatch here, which arrives at your LNA input. And then you adjust this balancing circuit to give you the same reflection, which is then inverted in this arm of the hybrid and arrives here to cancel out the leakage via the sort of transmit path. That can be fairly easily integrated. You can implement the hybrid as a transformer. It can be tuned because you've got this tunable balancing impedance. You can match the antenna impedance at different frequencies. And it has one antenna, which is an advantage. But you've got 3 dB loss because you've split the signal in your transmit path. You also split it, any signal that arrives at the receiver. So that's a big disadvantage. And there's no channel filtering as well. So we've looked at a few different ways of combining these different cancellation technologies and antenna interfaces. I'm going to go through a couple of those now. So just to recap, here are the different antenna interfaces and cancellers that I've just described and their advantages and disadvantages. The first thing we looked at was, well, could we take the electrical balance duplexer, which has, the advantage of having a single antenna. It's tunable, it can be integrated. It does passive cancellation already. Could we combine that with active cancellation and do this? The rationale for doing this was that we wanted to limit the complexity of this balancing circuit, which meant only being able to cancel in a single frequency band using the electrical balance duplexer. So we said, okay, let's tune that canceller to the receive band to cancel the noise. That's the passive canceller, so we use that for the noise. And then combine it with an active canceller to cancel the transmit signal in the transmit band. And you end up with something that looks like this. So that's your original transmit spectrum with the in-band component and the noise at this point at the PA output. The electrical balance duplexer cancels out the noise at the receive frequency, leaves you with a self-interference spectrum that looks like this. You've cancelled the noise, but you've still got this blocker. But you've got some suppression from the passive canceller. It doesn't not work at all. It just doesn't give you enough isolation. We've then taken a copy of the transmit signal and processed it, upconverted it with another radio to give you self-interference cancellation spectrum like this. It's got its own noise sideband, which you then need to filter out with a tunable filter to give you this. And you add those together and you cancel the noise in the transmit band as well, hopefully without desensitizing your receiver. We built this. This was several years ago in work that I was doing at the University of Bristol before I founded the company. And it basically works. That's some measurement results. That's the cancellation, frequency response of the electrical balance duplexer. So you can see you've got good cancellation in the receive band, not such good cancellation in the transmit band. And then we used our other radio to do cancellation in the transmit band. And so after the electrical balance duplexer, this was our self-interference spectrum in the transmit band. It was transmitting at above 23 dBm. And so we had 35 dB of isolation from the electrical balance duplexer at that frequency. So we had about minus 10 dBm residual self-interference. The active canceller took that down to minus 32 dBm. And that essentially met all the requirements for the level of transmit to receive isolation that we needed. That was more than 55 dB in both bands. But I think one of the obvious problems you can see with that is that it's really complicated. There's an extra transmit chain. There's two types of cancellation that need to be tuned. And even more significantly is the fact that you need to put something in here. You need to add a radio, and you need to make changes in the digital baseband. And so from a commercial perspective, that's quite difficult to do. You need to be a company that has access to the entire modem and RF system, or you need to be able to work with all of those companies in that whole ecosystem, which makes it quite difficult to introduce into the market. So we looked at this again and said, okay, what's a simpler way of doing this? Let's try the duplexer, tunable duplexer with a passive canceller. And that looks like this. So much simpler. You don't require any signal processing or any really significant signal processing in baseband DSP. You require some basic functionality to tune the canceller in order to select the different frequency bands, and same with the filters. So much like the RF front end is doing now, you program over a MIPI interface to select a frequency band. At the moment, that's selecting between some switches and a fixed duplexer. In this architecture, we're selecting between some settings for some tunable capacitors, which will tune the filters and tune the canceller to provide cancellation at that frequency. So this is what we've set out to build a product around this type of technology combination. And our module, that's the block diagram of our module. So you can see we've got the tunable filters and the canceller, but we've also combined this with a PA and an LNA and a coupler and some switches. And the reason for that is that gives us the same electrical interfaces as products that are already in the market. So mobile phone makers are typically not buying, one duplexer here and another one here and a set of switches. More often they're buying a whole RF front-end module that's integrating multiple filters and switches to implement a multi-band RF front-end module. So we're taking the same approach with the same interfaces, which essentially means we have a drop-in replacement. The module is 6x4, 4.5 millimeters, and I can show you some measurement results. We've got our first hardware prototype module implemented. You'll see it's quite small. And here are some measurement results tuned for a particular band, measuring the S parameters of the duplexer on its own. And that's showing you that we've got more than enough cancellation that we're achieving, as well as acceptable losses in the transmit and receive bands. And in terms of the specification, we can support all of the frequency bands below 1 gigahertz, with the exception of a few down at 400 megahertz that no one really cares about. And we've got similar RF performance to RF front-end modules that are in the market today. So that's essentially our value proposition, is more bands in a smaller size with virtually the same RF performance. So that's more or less everything I had to say. Just to conclude, we're targeting the replacement of SAW and BAW filters in mobile user equipment using self-interference cancellation. And we're able to cancel the transmit noise in the receive band as well as the in-band transmit signal using our patented combination of tunable filters and passive cancellation. And that means we can support more bands in less space. Thank you very much.
Thank you very much, sir. That gives us a lot to talk about. One question, and then we'll have to go for lunch.
You highlighted how the HIT actually limits what is available in the market at the moment with enhanced cancellation capability. What about power consumption? Did you have given that you're working with battery powered devices, how's your power consumption compared to the current market?
The cancellation hardware doesn't consume very much power. The PA, so whether or not we are competitive on power consumption comes down to whether or not we can get the same transmit insertion loss. That's the main factor, which then affects the overall module transmit efficiency. If you compare our solution against one duplex filter, we're not competitive. We can't get the same transmit insertion loss as a single filter. But when you're looking at a module that's got several frequency bands that it's trying to support, the losses of all the switching hardware really adds up. And when you compare us against that, we're competitive on module efficiency.